All right, everyone, welcome back to Calculus 2. So before we get going here, I have a few announcements to make about what's coming up. So 1 week from now, we're going to have our third midterm exam. So our third midterm exam is going to cover everything we did about power series, and then it's going to cover today's and Wednesday's lesson as well, which will be on parametric equations. So that will be exam number 3, and it'll be this coming Monday here. Let's see here. Was there something else that I was going to announce? What was that? Oh, yes, thank you. Actually, yeah, that was what I was going to answer or announce. Yeah, so I put up a practice exam 3, so you guys can go ahead and take a look at that. And I also put up some old exam 3s as well. Although watch out for those, because those include stuff on polar coordinates as well. And those won't be on exam 3, although those will be on the final exam. But yeah, so don't necessarily worry about the polar coordinate stuff there. All right. Oh, yeah. And then when will the list of power series reps we get re-released? That's already up on the miscellaneous section. So you can look at the equation sheet you guys are going to get for the exam. Okay, I think that's everything I wanted to say. Let's go ahead and get started here with our lesson. So the final part of the course is essentially going to get us ready for Calculus 3, because that course is kind of jam-packed. So there's not really enough space to kind of introduce this stuff. So we're going to learn it now. And don't worry, they'll review all of this when you do get to Calculus 3, but they won't spend a ton of time on it. So we want to kind of lay the foundation right now. So the first thing we're going to talk about are things called parametric equations. Now, what are these? Well, before I introduce what these are, I kind of want to review what we are familiar with, which are dependent and independent variables. Dependent, independent variables. So usually when we want to represent like a graph or a function, we write it as y equals f of x, right? And y is said to be the dependent variable, and it depends specifically on whatever x is. So effectively what we do is we choose what x is right here. Up the mic's crunchy. It's always like right in the beginning of class. Okay, hopefully that's better. All right, so we can select what x is, and then depending on what we select from x and what this function is, then we end up getting what y is right here. Now, this is all well and good. We've done a lot of things with functions written in this form. We can graph them by plotting the x value, and then it's matching y value on the vertical axis. But the thing is that there's a particular restriction with graphs of functions. Does anyone remember what criterion that graphs of functions need to satisfy? There's some kind of test. Yeah, it's the vertical line test. That's right. So what that says is that anywhere we should be able to draw a vertical line, and it should pass through the function at most once. Because what would happen if it passed through twice? Like, let's say the curve also kind of looked like this too. Well, then what that would mean is that there would be 2 different y values for the same x value. And that's not how this works. What we do is we pick an x value, and then there's one and only one y value that gets associated to the x value. So that's what the vertical line test is testing for, to see if any of this business is happening. But provided we don't have any of that, and any vertical line goes through the curve at most once, then we're good to go. Now, we've also been able to draw things that don't quite satisfy this. Like, for example, we're still able to have an equation for this shape, the circle. If we want to draw the unit circle, we could still write that in terms of x and y. That's just going to be x squared plus y squared is 1. Now, this doesn't satisfy the vertical line test, so it's not a function, but we can still write it in terms of our traditional x and y variables here. So even if it's not exactly a function, we're still okay with dealing with it. But what happens if we end up getting weird looking things? Like, what if we get something that kind of looks like an old-fashioned phone cord right here? So what if we want to write this in terms of x and y? Well, to be honest with you, I have no idea how we would write this in terms of x and y. Eventually, we're going to get to some shapes that are kind of confusing and a bit difficult to represent the traditional way. So what we're going to do instead is we're going to remove this dependency on the vertical line test. What we're going to do is instead of y depending on x, we're going to sort of equalize them. So x and y are both kind of on the same level, and in turn, they both depend on a new variable, which is usually called t, although sometimes it's called theta or s, maybe sometimes u, but usually t. So these are the dependent variables now, and then t is the independent variable, and it also has a special name. It's the parameter right here. So t is called the parameter, and then we have x and y depend on this parameter right here. So this gives rise to what are called parametric equations. And what these are is we have x being one function that depends on t, and then y can be a totally different function that depends on t right here. And because they don't depend on each other, we don't have to worry about the vertical line test. We can get more than one x value matching up with a y value, and that will actually free us up, surprisingly, like by a large amount, to draw things that look maybe like this or maybe even crazier than this here. During a normal semester, I like to have what's called like the parametric and polar art day, where we look at really kind of crazy looking curves. Maybe we'll have time to do that in a little bit. Well, we'll see. All right, so what we're going to do today is we're going to get comfortable drawing familiar shapes, maybe some not so familiar shapes, with parametric equations right here. And then next class, what we're going to do is we're going to learn how to do calculus with parametric equations. But for now, we're just going to get comfortable with these. All right, so here's my first example here. I want to show you guys how to do this. Example 1, find parametric equations. And I'm going to abbreviate parametric as parm from now on. Parametric's too long of a word. Find parametric equations that represent the line that passes through -2, 0 and 4, 3. Then convert these into the form y equals f of x. We want to find parametric equations for our line, and then we want to see what kind of normal or Cartesian equations represent here. What are the parentheses next to t? These are some other names for parameters. So sometimes instead of t, we use theta, s, u. These are some other common names, but t is probably the most common one. Yeah, parm. Yeah, it is like Parmesan. I think about that every time I look at this. All right, so let's go ahead and try this. So first of all, in order to know what a line is, we should probably be aware of what its slope is. So let's try to find the slope of this line right here. All right, so let's see. So the slope is the change in y, or the rise, 3 minus 0, divided by the change in x, or the run. So 4 minus -2. So we end up with 3/6, or 1/2 right here. So there's our slope. And then what we're going to do to make a line, so here are our line equations. We're going to have x of t be t plus a, and then y of t be mt plus b. And what are the a and b? Where a and b is a point the line goes through. Okay, so that means we actually already have all of the ingredients we need to write down the parametric equation for our lines. So x of t will be t, and then I guess I could pick one of these points to use. Maybe I'll just pick this one right here. So I have x, I have t, and then I add a, which is -2. So I have t minus 2. And then y of t, that's going to be the slope, so 1/2. And then I add in the y coordinate, but that's just 0. So these are parametric equations for our line right here. Now, the thing is you might be wondering, okay, well, we use the point -2, 0, but it also goes through the point 4, 3. So wouldn't these also work? Let's say we had x of t is t plus 4, and y of t is 1/2 t minus 3. It turns out that, yes, those would work as well. And this kind of illustrates our first sort of weird property about parametric equations. There may be more than one set of equations that represents the same thing. So both of these represent the line with slope 1/2 that go through these 2 points right here. And it's not just, oh, -3, sorry, I'm in +3. Thank you. All right, and it's not just these two either. I could pick any point in between here that's also on the line and also have that as well. So here are our line equations. Now let's convert this into our normal x and y. How do we do that? Well, what I'm going to do, I'm going to maybe start with these. I'm going to add 2 over here. So x plus 2 is t. And then what I'm going to do is I'm going to plug in this t into here. So this gives me that y is 1/2 times x plus 2, or 1/2 x plus 1. So this is going to be my normal line equation in terms of Cartesian coordinates without having a parameter right here. Can I go over how I got the x and y again? Yeah, sure. So to make a line, the formula is this right here. We have t plus the x coordinate of a point we go through. And then for y, we put the slope times t, and then we add a y coordinate that we go through. So I used the point -2, 0. So I had t, and then I added -2. And then my slope was 1/2, and then I added in 0 right here. So technically I should have had a plus 0, but we really don't need that right there. That's how I got my line equations. And this will work for any non-vertical line. What if we have a line that's just going straight up and down? So if we have a line that's just going straight up and down, then what we're going to do is we're going to have x of t equals a, where this is the x coordinate of the line, and then y of t equaling t. So you have a vertical line, it's going to follow this rule instead. So there's not going to be a t at all for the x right here. All right, do you recommend just using the points it gives us to make our equations? Oh yeah, there's no point in trying to find something in between there or anything like that. Yeah, just go ahead and use the ones that they give you. All right, so for our next problem here, I want you guys to give this a try now. So practice 1. Suppose a line L goes through the point 1, 2 and has a slope of -3. Find parametric equations for the line that goes through the same point but is perpendicular to L. All right, so go ahead and give that a try. So it needs to go through the point 1, 2, but it's going to have a different slope because it's going to be perpendicular to the line that had a slope of -3. And as always, we'll go over this in a minute. Is the final equation in slope-intercept? Yeah, this is in slope-intercept right here in terms of without the parameter. Yeah, what's up? So I solve this for t. So I add the 2 over and I have x plus 2 is t. And then I substituted that into here. So I have 1/2 times the x plus 2. What does it say in the last line? The line that goes through the same point but is perpendicular to L. The new slope be +3? Not quite. All right, let's take a look at this. So we already know a point that this line goes through, right? And it doesn't really seem like it's going to be a vertical line being perpendicular to a slope of -3. That doesn't really strike me as anything vertical. So we're probably going to use these equations up here. So let's see here. X of t is going to be t plus the x coordinate for our point. So it's going to be t plus 1. And then y of t will be our slope, which I'll write in a moment. And then we have t plus 2. Now let's see, how are we going to get our slope here? Well, the slope of the original line was -3, but we want something that is perpendicular to the line of slope -3. So if you ever want a slope of a perpendicular line, our new slope will be -1 over the old slope. So if we do -1 over -3, like this, then we end up getting 1/3 for our new slope. So this is going to be our set of parametric equations for this line right here. And like I said earlier, there's more than one. I mean, there's actually infinitely many different parametric equations for this line. We could have just put different coordinates that are on the line right here. But I think this one's the most obvious one because it's the point that they gave you right here. So these are given equations. Yeah, so the equations for any kind of line were given up here. So we have x of t is going to be t plus the x value of the point that we go through there. And then y of t is the slope times t plus the y coordinate of the point that we're going through. So when we look at this example again, we know we're going through 1, 2, right? The x coordinate is 1, the y coordinate is 2, so that's where we get these from. And then we just put the slope in front of the t and the y coordinate here. And that's all we have to do for any non-vertical line. And then for vertical lines, we just put whatever the x value is and then just a t for y right here. All right, how did I know to use the non-vertical line? equation because a vertical line can be thought of as having infinite slope, but our slope here is going to be 1/3. How did I get the slope? I knew I was looking at a perpendicular line, so it's the negative reciprocal of the slope that I was given right here. All righty. So in addition to lines, we could also have circles as well. So I'm going to go over more familiar shapes, and then I'm going to expand to shapes that are a bit less familiar. So for example 2, I'm going to find parametric equations that represent the unit circle. All right, so let's see here. I need x to be some kind of function. I need y to be some kind of function. Now let's see here. We draw our unit circle. Let's say we have a point x and y on the unit circle. What's usually the name for the x coordinate on the unit circle? What do we usually call that? It's cosine, right? So x is going to be cosine of t, or you might be encouraged to use theta for this, since we have an angle here. So either of these would be fine. And then you can probably guess what y is going to be. Y is going to be, I'm going to use t's, sine of t right here. So there we go. So we have some parametric equations that represent the unit circle. Okay, how can we be sure that these represent the unit circle? Well, the unit circle has the equation x squared plus y squared is 1, right? So if I substitute these into here, I have cosine squared plus sine squared. And as we all know, that's also equal to 1 as well. So these are going to be our parametric equations for the circle, or for the unit circle. Now, what we could do is we could generalize these equations a bit. So kind of like how I gave you the line equations, now I'm going to give you the general circle equations. So for a circle of radius r and center, I think I usually use h and k for that, we're going to have x of t be r cosine of t plus h, and then y of t is going to be r sine of t plus k right here. So we have an r on both of them. That's going to be our radius, and then we just put the coordinates for the center right here. So this is how we write down an arbitrary circle of any radius. And you can see how the unit circle is a special case of this, because the unit circle has radius 1, so these kind of go away. And then it has center, the origin. So these would both be 0, and these go away. So that's where we get the parametric equations for our circle here. Should we memorize this? Yeah, that'd be a good idea. I would definitely remember this. All right, so here's our second practice problem. I don't think this one will be too bad. Find parametric equations that represent a circle of radius 3 centered at 0, 1. All right, so I'll give you guys a minute to take a look at that. What do we get for the first one? Where did I put that? Oh, it's up here. Why is this test so close to exam 2? Hey man, I don't pick the dates. They just kind of give them to me. I wanted to have exam 3 be later, but yeah. When is the final exam? It's Monday, April 26th, I think. Can I keep my Cal 3 lectures up for next semester? Yeah, I'm not going to take them down or anything. All right, let's take a look at this. So find parametric equations that represent a circle of radius 3 centered at the point 0, 1. All right, well, all we need to do is just literally follow this formula right up here. So what's the radius? What's r going to be right here? We have x is 3 cosine of t, and then our h coordinate is going to be 0. So we just have 3 cosine of t. And then for y, our radius is 3. We have sine of t, and then we have k right here, which is 1. So there we go. These are our parametric equations for the circle of radius 3. All right. So it's that easy. You could use this formula to get a circle of any radius and any center that you want. Now, kind of like the lines, just because we have a kind of a nice formulaic way of doing things doesn't mean that that's the only way that things can show up. So I kind of want to show you how versatile parametric equations are in the next example. All right. So example 3, find 3 more sets of parametric equations for the unit circle. And I said 3 more, so it's going to be cheating to use the ones that we found earlier right here.
Professor, do you mind going up this a little bit, please?
What was that?
Can you just show the general circle equation one more time, please?
Yeah, it's right there. All right. So I want to find 3 more sets of parametric equations for the circle right here. So I can't use cosine and sine. I already used those earlier. So I need to find out some different ones. So let's see here. I'm going to use x is cosine of 2t and y is sine of 2t. And it turns out that these are actually going to be parametric equations for the circle as well. I mean, one thing you could do is you could just square these and add them together. So remember, the unit circle needs to satisfy this. So if we square these and we add them together, we end up getting 1. It doesn't matter if there's a 2t in there. All that they need is the same argument and to have the square of sine and cosine added together again. All right. So let's see here. What is the difference between using this and using the regular parametric equations we had earlier? Well, I'm going to explain to you now why we use t as a variable for parametric equations. T represents time in physics. Now, one way you can imagine these parametric equations is you can imagine them as the x and y positions of a particle moving along the curve at a particular time t. So if we look at this circle, we start here at t equals 0. How long will it take us to get around the entire circle if we use these parametric equations right here? How long will it take to get all the way around? Yeah, it'll be half of what the other equations took. So it's going to take pi, right? Because so if we imagine t is like an angle, then when we get to 2 pi, we've gone around the whole thing. But all we need to have here is t equals pi because we already have the 2 provided for us right here. So it's going to take pi seconds to get around the circle this way. we could draw arrows representing which way we're going around the circle here. Now, if we use the original parametric equations that I had earlier, if I draw the same picture, it's going to draw the same picture. It's going to follow the same path that the other ones did. But this time, it's going to take 2 pi to get around. So that's the difference between these representations here. They both draw the same picture, but they sort of draw it in different amounts of time. Now, in some applications, that's irrelevant. Sometimes you just want the picture and you don't really care about the physics end of it. So then, yeah, these are effectively the same then. But if you're modeling the position of some kind of particle or something like that, then these are actually going to be different. This one's going faster than this one is right here. And that's something we're going to talk a little bit more about next class. All right. So we found 1 more. We need to find 3 more. My next set of them, so this is 1. My next set will be x is cosine of negative t and y is sine of negative t. So once again, we could plug these into x squared plus y squared and we'll get 1. So it does map out the unit circle. But if we're imagining this as a particle moving around the path of the unit circle, what's the difference between this one and these two right here? It's going the other way. That's right. So if I put larger and larger t values in here, I'm going to start getting negative angles. So I'm tracing around the circle and I'm doing it at the same speed as the original one. I'm just doing it in the opposite direction. We could draw the arrows to represent that. So this one runs around counterclockwise, but this one goes around the circle clockwise. But it does it at the same speed that our original one did right here. By the way, another way of writing this, you may remember the cosine is an even function, so it swallows the negative sign. You may remember the sine is an odd function, so it spits out the negative sign. So you may also see it written like this as well. All right. So let's find one more way of doing this. This one looks a little bit strange, but it still works. Let's have x be sine of t and y be cosine of t. All right, now how is this one going to work? Well, again, it's going to draw the whole circle, but if we start at t equals 0 here, we have x is 0 and y is 1. So we're going to start here. If we plug in t is pi over 2, we have sine of pi over 2 is 1, cosine of pi over 2 is 0. So not only are we going around the circle backwards, but we're also starting in a different place. But nevertheless, it still gives us the circle right here. All right, so this kind of goes to show you that there are a lot of different ways of representing the same shape with parametric equations. And in some applications, like if you only care about the actual shape and not how it's drawn, all of these are interchangeable. You could use any of them. But if you care about the speed at which this is drawn out, or if you're doing physics, then each of these would be considered to be different right here. And when we get to calculus 3, there will be examples of both. There will be examples where you can use any one of these and it doesn't matter, or there'll be examples where we need to use a specific one of these right here. Can I use negative 2t? Yeah, sure. You can use any multiple of t. So you could have cosine of at and sine of at. These need to be the same, though. Whatever we put inside cosine and sine need to be the same, or else the Pythagorean theorem won't work right here. Do we know how fast 3 is going? Yeah, 3 is going at the same speed that the regular one and then 1 is. 2 is going faster than, or sorry, it's going the same speed that 2 and the original one are going at. Because it takes 2 pi to get all the way back around right here. All right. So there we go. So we could find a bunch of different representations for the same curve. All right, now I want to wrap things up for today by drawing out a curve that may not be so familiar. So far we've just looked at lines and circles, and yeah, we already know how to deal with those. You know, why are we even bothering with this parametric stuff if you know, we're just dealing with the same things we already know how to deal with? Well, here's something that is a little bit less familiar. So what we're going to do for example 4 is we want to sketch the parametric curve. X is sine squared of t, and y is 1 plus cosine of t right here. Okay, so this won't just be a circle because if this were just sine of t, it would have been a circle. But since it's sine squared, it doesn't really match up nicely with this right here. So this isn't going to be a circle. All right, now how are we supposed to sketch this out? What is it going to look like? Well, this might sound kind of stupid, but the best way of sketching this out is just plot points. So what we're going to do is we're going to make a table of t, x, and y, and we're going to plot points until we think we get an idea of what's happening here. So here's x, here's y. Why don't we start at t equals 0? That seems like a good place as any to start. So if I take t equals 0 and put it in here, I get 0. If I take t equals 0 and put it in here, cosine of 0 is 1, and then 1 plus 1 is 2. So it seems like at time t equals 0, if we're imagining that this is a particle, we're starting off right here. Okay, next, why don't we go to t is pi over 2? Let's see, pi over 2. Let's see, sine squared of pi over 2 is 1. And then 1 plus cosine of pi over 2, well, cosine of pi over 2 is 0. So it's 1 plus 0 is 1. So we end up right here. And then let's go to pi. Let's see. So with pi, we have sine squared of pi is 0. And then we have cosine of pi is -1. And 1 minus 1 will be 0. It seems like we're kind of coming around to the origin here. And how do I know which way these curves are bending? I kind of just always make them puffed out by default. These almost always end up being puffed out. So I'm going to draw them like this. All right, let's keep going. And if you're unsure, you could plot in points in between these. So if you're not really sure how it's going to behave from here to here, you can maybe plot in like pi over 4 if you ever want to get more detail in these. All right. 3 pi over 2, let's see what happens then. Well, sine of 3 pi over 2 is -1, right? But if I square that, I get +1. And then cosine of 3 pi over 2 is 0. 1 plus 0 is 1. So it seems like what we're doing is we're actually going back along the same way we came back to here. So it seems like we're coming back here, okay. And then what about 2 pi? Well, sine squared of 2 pi will be 0. And 1 plus cosine of 2 pi will be 1 plus 1 is 2. So it seems like we've made it all the way back here. So it takes pi seconds for us to go from here along this curve to here, and then another pi seconds for us to bounce back this way. So it seems like what's happening with this parametric curve is we're just bouncing back and forth along this parabola-looking shape right here. So that's exactly what's going on with this curve. So another feature of parametric equations is that you could draw curves that are only finite in scope. Usually with functions, we draw things that kind of like go on forever, or at least we assume they do. But with parametric equations, we can draw finite shapes like this right here. And I wish I had a better way of telling you how to graph these besides plugging in points, but honestly, it kind of is the best way. If you're unsure how it looks like, maybe plot in a point in between some of these right here. Now, you guys are lucky because you guys don't have any kind of paper exam, so you won't have to draw these. But we may ask you, okay, if we give you a certain parametric equation like these, then you have to pick out the shape that it ends up looking like right here. All right, now I actually want to show you something really cool that we can do with this in our last few minutes here. So let's see here. The sky's really the limit with what we can draw with parametric equations. And I want to show you what I mean by that. Oh, whoops, I need to go on Chrome first. Okay, let me share my screen over to the internet here. Let's see. All right, can everyone see Wolfram Alpha? It's okay? All right. So what we can do on Wolfram Alpha is we can draw parametric equations. So we can plot x of t is sine squared of t, and y of t is 1 plus cosine t. And then there we go. So we can end up getting a nice shape right here. So we end up getting this parabola right here. Now we could do this to draw even more insane functions. So like what we could do, we could just make something up that's like ridiculous. So let's do tangent of t to the 99. And then 1 plus, I don't know, let's do secant now. That sounds fun. Okay, so what's this gonna give us? Yeah, it ends up giving us some insanity right here. So these parametric equations, they have a lot of versatility. They could draw some really insane looking things right here. But probably the most fun part about this is that there exist parametric equations that depict the likeness of famous characters. So for example, we can plot the Pikachu curve here, and we end up getting this right here. So you could pretty much type in any kind of character name or any politician or famous person in here, and they'll end up having a parametric equation representing it. And you may be thinking, okay, well, what kind of equation is going to give me this this Pikachu looking thing? And it's going to be this. So we have all of these sines and cosines kind of stacked together here. And this is just the x. This is only the x half. So this is x. And then we get to y down here. All right, and you'll notice kind of spliced in here, we have these like little theta things. I don't know if you can see my mouse right now, but you'll see like these theta of 39 pi minus t, t minus 35 pi. These are sort of on and off switches. So when we hit 39 pi, this will turn off. But when we hit 35 pi, this will turn on. So that's how they were able to kind of make distinct lines for this right here. Okay. Da baby. They have a lot of things. They don't have everything on here. Yeah, they have Naruto curve. I think someone asked for Bill Clinton earlier. It's thinking about it. Oh, wait, what? They don't have him anymore. What? I know they have Hillary Clinton. I've done that one. Oh, it's coming. There we go. All right. Do they have Aaron Yeager? I don't know. No, it doesn't have it. Oh, well. Well, they have a lot of different stuff in here. So you can play around and have fun with this. I know they have all the Disney princesses and everything. But yeah, this is just kind of to illustrate what parametric equations can do. Now, we're not going to ask you to draw the Pikachu curve on the exam or anything like that, or memorize any of that. But I just want to show you that there's a lot of versatility in this here. All right, that's pretty much it for today. So I will see you guys on Wednesday, where we will learn to do some calculus for this stuff.
Professor.